A very good evening, ladies and gentlemen. We'll start the hangout in just a couple of minutes' time. If you know anyone that may well benefit from watching this video, then please do share it with them. Just waiting for a few more people to join, and we'll just start in about 30 seconds' time. Feel free to post any questions as you go through on the frog wall, and I'll answer them as I go through. Okay, good evening. We'll make a start on the chemistry paper 2 revision hangout. It is the night before the chemistry exam. So you'll be using this video as really a confidence boost to how much you know, so that you'll be ready for the exam tomorrow. As always, we're in the exam season, so do make sure that you look after yourselves, that you're eating well and you're getting a good night's sleep ready to transmit all that information you have in the exam tomorrow. Remembering also the couple of key tips for the exam. If there's something that you really can't quite remember, then brain dump it as soon as you get into the exam on some white space inside when they tell you to start. And make sure you have all of your equipment with you. You must have a pen, pencil, ruler, and a calculator for this exam. So let's get started then. Let's have a look about what's coming up in the exam. This is chemistry paper 2. So you can ignore pretty much everything from 1 to 5 that came up in topic 1. And we're concentrating on the rate and extent of chemical change, organic chemistry, chemical analysis, chemistry of the atmosphere, and using resources. So already tomorrow, when you know in the exam, you know that topics 6 to 10 are the ones that are going to be covered by the questions in the exam. So what I'm going to do is I'm going to highlight some of the required practicals that are going to come up tomorrow, because as you know, these feature quite heavily in your exams. And then I'm just going to go through the main content that comes up in each topic. If you really want a full version, you can have a look at the combined science or the separate science videos that I have uploaded. But this will go through the main content for you to prepare yourself tomorrow and to make you feel confident about how much you know, because you've been revising for a long time and you do know your stuff, and this will just hopefully reassure you of that. So, required practicals for paper 2. You might expect to see paper chromatography in there tomorrow, or concentration and how that affects rate of reaction. You could see a required practical on the analysis and purification of water. And for separate science, expect identifying ions, the required practicals that are surrounding that, to come up in your exam tomorrow. Let's start off then with I'll do this one later on for the separate only pupils, but let's start off with the required practicals for both combined and separate scientists. So paper chromatography, it is a way to separate coloured compounds. So the chrome links to colour. It tends to be coloured compounds that we are separating by chromatography. This is paper chromatography. You need to know about how to set up the practical. You might be asked a method for that. So we've got the solvents. That can be water, but it can be other liquids, and that can affect how high the particles move up the water, move up the paper. We've got our solvent, some kind of liquid in the bottom. We've got a piece of chromatography paper. Onto that, you will draw a line in pencil, because you don't want that line to smudge up the paper. And onto that line, you will put your sample. So it could be that you're looking at food dyes, or other dyes that go into clothing, You could be looking at taking particular food samples out of things to test them in some way. It could be absolutely anything that you want to test. It could be a pen dye or something like that. You would then put a blob of that on your chromatography paper, on your pencil line. So that's where we've put the dyes. And the particles in the dye will dissolve in the solvent and move up the paper. But they will interact with the paper in different ways. So some will move only a little distance. Some of the particles that are in that dye will move further and further and further and so on. And then at the top, you will get a line called the solvent front where the solvent will move to and stop. So this way we've got our dyes here and they have separated out. So if we had, for example, a known banned substance that was X, we could put that on our paper and we can, the key thing is compare it to our patterns that we see in our other dyes and see if it's present. So you can see here, this matches there, but not there, and this matches there, but not there. And you would compare them to see if they had the banned substances. A pure substance wouldn't separate out. A pure substance would literally just go up and you would see one dot. You have to put a lid on it. This could be a question that they ask on how to improve the practical tomorrow. You have to put a lid on it to prevent the solvent evaporating. It would be nice if that question comes up tomorrow. This is a calculation in relation to this practical, and you calculate an RF value for each of the dots that you get on your chromatography paper. So I've just put them as little lines here. At the top, we would also have a solvent front to show where the solvent had moved to. So I'll just draw one on there. Let's say the solvent had moved to there, which is this line over here on this diagram. Then to measure the RF value, we would measure the distance travelled by the substance. So from the middle of the dot downwards, measure that with your ruler. And then you need to measure the distance travelled by the solvent, which is from the solvent front down to the line. And then you simply do distance travelled by the substance divided by distance travelled by solvent. So let's say, for example, this was 10 centimetres and this was 5 centimetres. You would then do 5 divided by 10 and you'd get an RF value of 0.5. And you do that for each of the substances. So don't forget, middle of the dot down and measuring to the solvent front. So that's one required practical that may well come up tomorrow. Another required practical that you may well see tomorrow, well, there's two for this one. It's all about concentration versus rate of reaction. So there's two different practicals that you might see. This one here, we've got a metal and an acid. And when we react these two together, we make a salt and hydrogen. So this here is showing hydrogen gas being released. This is an observation that we can make, that hydrogen gas is released. And you can see it's on a balance showing 25 grams. As this reaction will start, there's no lid on at the moment. So the hydrogen will leave and the mass will go down. And what you can do is you can record the mass, record this at regular intervals, say every 30 seconds, and you can use that to measure the rate of reaction. So you can do the amount of reaction used over time. This equation here, the mass used up over time. Then you can change the concentration of the acid you're using. So this could be your independent variable, and you're changing the concentration of acid perhaps from 0.1 to 0.5 to 1 each time. The other way of doing this one is to add a bung and a syringe to the conical flask, and that can collect the gas for you. And if you use a gas syringe with measurements on, the plunger will move back. So that will move back to here, say, and this volume of gas will tell you the volume of gas made. So rather than just doing that once to measure the rate, again, you do that every 30 seconds, and you could measure this time the amount of product made, the volume of gas made over time. The other concentration versus rate of reaction experiment that you might see is to do with looking for a precipitate being formed. Precipitate just means a solid being formed. And this is when into our conical flask, we would add sodium thiosulfate and hydrochloric acid, or any acid really. And that will form a precipitate. And what that will mean is this solution will gradually go cloudy. So it will build up with a solid precipitate and it will go cloudy. So if at first we could see through that conical flask, because the solution was colourless, we would be able to see the cross that is on the piece of paper or the white tile beneath it. We'd be able to see that. But gradually, over time, as this reaction happens and it goes cloudy, that cross underneath will no longer become visible. So what can we do? We can time how long it takes for the cross to disappear. And then we can change the concentrations that we're using. We can change it to 0.1, 0.5, and 1. However, this time it's really difficult to use these equations up here because we're not measuring a mass change and we're not measuring a volume change. So this is where that weird equation comes in, where we calculate the rate by doing 1000 divided by time. And our rate will be per second. Okay, so if we can't physically measure how much product or reactants are being made or lost, we're measuring a colour change or the time it takes for it to go cloudy, we must use this equation instead. The next required practical that you might be asked to look at, and the final one for combined science, is to do with analysis and purification of water. So this whole process that we're talking about here is distillation, where we can take something like salty water in here, or it could be an inky water, hence why I put the green in there to start with, but let's say it's salt water. We can put that in there, we can heat it up, and we will evaporate it, and then we will condense it. And in here, we should be left with our salt, and in here, we should have pure water. So the steps we need to do, first of all, we need to test the pH of our salt water using a pH meter. We must use this because we can't add an indicator in. If we add an indicator in, it's a bit pointless because it's just going to be another thing that needs to be separated. So if you use a pH meter, which is a device that you would stick into your solution and measure the pH electronically, that is a better option. If it's too acidic or too alkaline, we would then neutralize that by adding either an acid or alkali, depending on what it needed. We would then do this process here, which is distillation. And we would then, with the pH meter, just retest the pH at the end to make sure it is pure water at pH 7. If you are doing combined science, what you need to say is that you check at the end to make sure there is no salt crystals, or there are no salt crystals, I should put. Make sure there are no salt crystals. That means you know that it's a pure water that you've got at the end, which will then be suitable for you to drink because you can't drink salty water. However, this is important for separate scientists because this links into the identification of ions. What they would want you to do at the start, so if you do the hour and 45-minute exams, listen up for this 30 seconds, you would want to test the salt at the start to make sure you have sodium chloride. So I'll talk about this later, but you can think about the flame test that you would use and the test for the halide that you would use to prove that it's sodium chloride in the water. And then at the end, when you retest the pH, you would then also retest for sodium chloride. So bear that one in mind, and I'll link that to your practical later on. So that's the required practicals done: chromatography, rates of reaction, and distillation. Now I'm going to go through a few of the key areas that will come up in each of the chapters in your exam tomorrow. So topic 6 is the rate and extent of chemical change. So we've got some particles over here on the left-hand side, and those particles would be moving around all of the time, just randomly, random motion of particles. But only if they have enough energy will they actually react. And this minimum amount of energy that they need is called the activation energy. It's the minimum amount of energy needed for a reaction to happen. So if these two collided and they had the activation energy, which is enough energy, then they will collide and react. There's several different things that we can do to change the rate of reaction. We can increase the pressure. That will increase the rate of reaction. We can increase the concentration, and so will that. We can increase surface area, increase temperature, and we can add a catalyst. All of these things, let's start with these ones first of all and leave the catalyst alone for a minute. All of these things are linking to collision theory and the idea that the particles are colliding because they increase the frequency of collisions and they increase the rate of reaction if you increase them. This is super important because it's the same words for all of them, which is nice. You must be putting, if you increase the pressure, you increase the frequency of collisions, which increases the rate of reaction. Same for concentration. Increasing the concentration increases the frequency of collisions, increases the rate of reaction. This one here, and same, sorry, for surface area and temperature. This one here is for gases. Okay, pressure is to do with gases. Concentration is to do with solutions generally. Surface area is to do with solids. So, for example, if you had big pieces of something like calcium carbonate, to increase the surface area, you would smash it up into a powder, and that is going to give you a quicker rate of reaction because there's more area for the particles to collide with each other, and it increases the frequency of collisions and increases the rate of reaction. So think about the situation that they give you. If they say, what would you do to increase the rate of reaction? Or think about whether the experiment talks about a pressure, whether the experiment talks about a gas, a solution, or a solid. Temperature needs a couple more things. Yes, if you increase the temperature, you increase the frequency of collisions, increases the rate of reaction. I mean, repeating that again and again on purpose. But they also cause the particles to move more energetically, and therefore the particles move faster. Okay, so you're actually putting energy into this one, so you're going to have particles moving with more energy and the particles are moving faster, but you must also include these 2 points in your answer. A catalyst, a very specific definition for a catalyst. It provides, see if you can think about it before I even finish writing it, it provides an alternative pathway with a lower activation energy. That links back to the topic in topic 5 when they had those reaction profiles, something that might have looked a little bit like this, and there's the activation energy on it. So the catalyst, the effect of a catalyst would look something like this, because it's a different pathway and it's got a lower activation energy. So these are the keywords that you need to get in. Also in this topic is reversible reactions. This here is the symbol for a reaction that is reversible. This is a key one that you have to know. Something called hydrated copper sulfate. And the clue here is hydrated, it's already got water in it. And this bit starts off as a blue powder. Think water is normally associated with the colour blue, so that starts off blue. If that is heated, there's an endothermic reaction in this way because there's only one thing here. It's broken down by heat and it makes anhydrous copper sulfate and water. The opposite reaction is exo. With reversible reactions, if it's endothermic in one direction, it is always exothermic in the other. So this one is thermal decomposition. Something's being heated up, broken down into two things. This then releases the water as steam, and then you end up with your anhydrous copper sulfate, which is white. So you need to know the colour changes. The hydrated copper sulfate is blue because it's got the water in it. Heat it up, it breaks down, the water gets released, and you end up with white anhydrous copper sulfate. If you then add water to this and react them together, then you'll end up with the blue stuff again, the hydrated copper sulfate, because it is reversible. Still on topic 6 then, rate of reaction. You might be asked to draw a graph for rate of reaction using data provided, or you might be asked to calculate something from it. So for example, what is the mean rate of reaction? So you need to look where the reaction stops. So about this point here where it starts to flatten out, the reaction has stopped. So with a straight line, unlike what I've just done, on your graph you would draw a line going across and a line going down. So let's say that this here, my graph's not very accurate, but let's say this here was 15 seconds for the reaction to stop. And in that time, let's say it produced 33 centimeters cubed. To calculate the mean rate of reaction, we do the amount produced over time, which would give us 2.2 centimeters cubed per second. So the rate is the amount produced slash time. They might ask you for the mean rate of reaction between 4 and 12 seconds. So what you would do then, let's see if I can do it with a line instead. You would go up at 12, like so, and across. And you go up at 4, like so, and across, showing you're working on your line. So the mean rate of reaction between that time, well, you just need to see how much gas it is produced over what time. So this is between 20 and 32.5. So that's produced 12.5 over 8 seconds. So that has a rate of reaction of 1.6 centimeters cubed per second. For higher tier, I'll go through it in a minute, not now, but you will need to do something extra because you will need to be able to draw a tangent to these curved lines and calculate the rate that way. But I'll go through that when I do the higher tier content a little bit later on. So, storming through then, topic 7 is organic chemistry. Organic chemistry talks about molecules that are carbon-based. And these here are hydrocarbons. The clue's in the name. They contain 2 elements from the periodic table, hydrogen and carbon. One little tip to try and remember how to name these is if you remember all of the time, monkeys eat peanut butter. Monkeys eat peanut butter. And these are all called alkane hydrocarbons. So they all end in ane. So this one is called methane, ethane, propane. Propane. Just rub that a little bit out. And butane. Let me just do propane again. Okay, with these molecules then, 1, 2, 3, 4. It has to be in this order because methane has just 1 carbon, ethane has 2 carbons, propane has 3 carbons, and these are saturated molecules. They are full of hydrogens. You can't fit any more around them. So we say they're saturated. That means they're full of hydrogen. All single bonds. And we can write the formula for them. So this is the displayed formula. This is the drawing. Each line represents a bond. So this would be C, because there's one of those, H4. This would be C2, H6. This would be C3, H8. Because the rule is the general formula for an alkane is Cn, H2n plus 2. So that means for whatever number of carbons you have, you double it and then add 2, and that gives you the number of hydrogens. So you might be asked to draw a molecule, for example, butane. You should now know that that's got 4 carbons. So you would do C4 and double 4 and add 2 will get you 10. So C4H10, and we draw that out by doing 4 carbons, and then all of those will be bonded to hydrogens, so they are full up. So these molecules are found in crude oil. Crude oil is a mixture of hydrocarbons. This is made out of dead marine organisms over millions and millions of years under deep pressure under the oceans. And we drill down through the oceans to extract crude oil from below the seabed. These are really important because these are useful fuels. For example, this reaction here is called a combustion reaction. When things combust, they react with oxygen. So we've got methane plus oxygen, and it always makes carbon dioxide plus water. And this is complete combustion. Everything combusts properly. There's enough oxygen, and we're making carbon dioxide and water. And that'll be the same for anything. Ethane plus oxygen would be carbon dioxide and water. Propane plus oxygen will be carbon dioxide and plus water, etc. So these are the only 4 you need to know. If you remember monkeys eat peanut butter, that will give you the right number of carbons. These can then be put into a fractional distillation tower to be separated because, as I said, crude oil is a mixture of different hydrocarbons. So some like methane will be short, ethane a bit longer, propane a bit longer, butane a bit longer. But then you also get really, really long hydrocarbons, and they need to be separated. So they put the mixture in and they heat it. So it's hottest at the bottom and it's cooler at the top, away from the big furnaces and the fire at the bottom. At the bottom of the tower, think about what molecules come out. Think about what words you would describe for those molecules. Feel free to pause the video and come back if you want to. We've got long ones coming out the bottom. So the longest chains coming out the bottom, they have a really high melting point, high boiling point, and they are really viscous. They are thick. That means they're thick and they don't flow easily. Thick and gloopy. At the top of the tower is where you get your really short hydrocarbons and longer, and so on and so forth. So here we have our shortest molecules. I'll put here that these are long. These are the most useful fuels. They are flammable, which means they can get alight easily. They are volatile, which means they turn into a gas easily, and they have a low melting point. The words for inside then, as we're heating it, these fractions, when they reach their melting point, they will evaporate. When they reach their boiling point, when they reach their boiling point, they will evaporate and turn into a gas. And then they will rise up the tower, and as they do, they're cooling down. So when they reach their condensing point, they will condense and they will come off of the tower as a liquid. So they'll evaporate and then they'll condense and come out as a liquid. So they're really useful fuels. You get things like petrol come off of these, and you get things like diesel and loads of other different fuels as well. You don't need to know the names that come out. So products can be useful fuels, but they're also used in other things. We call them feedstocks, which means they can feed other chemicals, really. They're used in other chemicals. They're feedstocks for chemicals such as solvents, lubricants, plastics. They go on to make polymers and things like that. If you notice here, we've got diesel here. Diesel is a really long chain hydrocarbon compared to petrol. So sometimes we need more petrol when we've got lots of diesel. So what we can do is a process called cracking. And with cracking, you use a lot of heat and a catalyst, often, not always. We can have steam cracking as well, but if we've got catalytic cracking, we're using a catalyst. Heat and a catalyst to break the long molecules into shorter ones. And they could break anywhere. So let's take this as an example. We could break that molecule here, and it would make an alkane and an alkene. So alkene and an alkane. So let's say, for example, this one is going to be our alkene. Let's take the 3 carbons, but this one's special because alkenes have a double bond. So 1 double bond and then the rest single. And filling it up with the hydrogens, that's already got 2 bonds, so that can only have 2 more. That's already got 1, 2, 3 bonds, so that can have 1 more. And that can have 3 more. So there's our alkene. It's got 3 carbons, so actually that's propene that we've made there. And the other product will be an alkane. So 1, 2, 3, 4, 5, filling that up with the hydrogens, like so. And you can crack it anywhere. They might ask you to complete the diagram for one of these. So the cracking gives us 2 products. It gives an alkene, and this can go on to make plastics and polymers and things like that. And we've got another alkane, which could be a shorter chain, which might help us meet the demand for petrol. So this is all to do with how much we can supply and what the demand is for it. So expect to see those words associated with petrol and diesel or other fuels. So take a long chain, heat it up. If it's catalytic, you put it over a catalyst called aluminium oxide and heat it up, and that will crack the chain into your alkane and your alkene and alkane, that way around. And if you have a steam catalyst, that is using steam and heat. The vate is heated up and it's passed over steam, and then that will crack it. So that's topic 7 done. Feel free to take a breather if you need to. You can always pause it and come back later on if it's too much content all at once. But we'll move on to topic 8. I have seen a question on the frog wall, so thank you very much for that. I'll come up to that in the separate only content. If you do have any more questions as we go through, please feel free to post them on the frog wall. So, topic 8 is chemical analysis. It's quite a short topic, really. You need to know the tests for 4 different gases. So, hydrogen is the squeaky pop test, where you would put a lit splint into the test tube full of gas. So you'd have your test tube with your gas in it, and you would put in there a lit splint. And if it goes pop, you know that you have hydrogen inside. For oxygen, you would have your gas in the test tube, and oxygen relights a glowing splint. So you would have your splint, it would be alight, you would then blow that out, and then you would put your splint in there, so it's just a little bit glowing now, and it's not fully alight. If oxygen is present, that will cause that splint to relight, and you know that there is oxygen present. Carbon dioxide, you would bubble. So say you had your reaction in this conical flask here, connected to a bung and a delivery tube, you would bubble that through lime water. And if lime water goes cloudy, that means that carbon dioxide is present. Because precipitate forms, it goes cloudy. So a bung, delivery tube, lime water goes cloudy. And chlorine, if you're testing for chlorine, that bleaches damp litmus paper. So you would hold, or you would have your test tube perhaps with your gas in there. You'd put your litmus paper into that to test for the gas, and then if that started off blue, that would go white like that and bleach where the chlorine hits the litmus paper. So those are the 4 tests that you need to know about. You need to also know about pure substances. If I just move this along here a minute, it works. Okay, you need to know about pure substances. They're substances that only contain one element or compound. So, for example, if you had a beaker full of just water, just H2O, that contains one compound, so that is pure. Anything else in it, and it's not pure anymore. If you had one bottle containing just the element oxygen, that would be pure. However, if you didn't want pure substances, you might want a very particular recipe of different chemicals for a particular purpose, and that is called a formulation. It's got the word formula in it, so it'll have a particular formula or particular recipe depending on what you want. The difference between the two then are pure substances have a very particular melting and boiling point. So, for example, if you were testing to see whether a sample of copper is pure, if it had a melting point of exactly 1083 degrees C, you would know that that was a pure substance of copper. Any variation in that, and that means it's not pure. You'll have impurities in it, other atoms, other elements that are not copper, which is affecting the melting point. So they might ask you to look at some results, compare them to the true constant values of melting and boiling points, and ask you to work out whether something is a pure substance or it is impure. If it's impure, it doesn't mean that it's a formulation necessarily, because a formulation is a very specific recipe for a specific purpose, like a paint. A paint, you're going to put certain ingredients into that to make your paint, certain chemicals and certain percentages. Fertilizers as well, when we talk about NPK in separate science, you don't need to know that for combined, but those fertilizer formulations, because they have very specific percentages of chemicals inside. So, moving on then. Chemistry of the atmosphere. So this is topic 9. The main things that come up in topic 9 is the evolution of the atmosphere. So the idea that once upon a time, several billion years ago, our atmosphere was very much like that of Mars and Venus is today. It was full of carbon dioxide, chucked out by the volcanoes, nitrogen, ammonia, CH4, which is methane, and water vapor. So it is very rich in carbon dioxide, whereas now carbon dioxide is one of our trace gases. There's only about 0.04% of carbon dioxide in our atmosphere today, when there's around, but in the exam they'll probably say 20% of oxygen and round nitrogen up to 80%. But you know, pretty much all of it's nitrogen. A good whack of it is oxygen, and then there's some trace gases which include things like argon, which is a noble gas, and a very small amount of carbon dioxide. What you need to know, maybe a 6 marker, maybe an extended answer question, is how the atmosphere has evolved. First of all, this water vapor that was produced condensed to form the oceans. And this was really the start of where a lot of this carbon dioxide went. So the carbon dioxide, after the oceans were formed, started to dissolve into the oceans, and then it got locked up. It got locked up in things like sediments, which made sedimentary rock. It got locked up in the carbonate shells of animals. Eventually, over several millions of years, it got locked up in fossil fuels. So it's going away from the atmosphere and down into the oceans and getting locked up in rocks, shells, and fossil fuels as carbonates. Then came the evolution of the plants. So algae and plants, they both photosynthesize. And in photosynthesis, they take in carbon dioxide and they give out oxygen. So again, we got more carbon dioxide being locked up in plants as part of photosynthesis, and also we get this oxygen which is starting to be released into the atmosphere, increasing the concentration up until around 20% in our atmosphere today. Still on topic 9 then, we've got chemistry of the atmosphere. So this picture here is depicting the greenhouse effect. So the greenhouse effect is what causes global warming, all to do with mainly carbon dioxide, but also methane and a bit of water vapor. So in the atmosphere here, we have got carbon dioxide, some methane, and also, to a lesser extent, water vapor as well. But what they do is the rays from the sun that go into the earth are shortwave radiation. And what happens is the shortwave passes through the gases in the atmosphere and goes to Earth. However, when it comes to Earth, it's absorbed and re-radiated by different objects, and it's a longer wavelength that goes back. So short goes through, and then at the point of contact with the materials on Earth, long wave radiation is re-radiated back out. But that cannot pass easily through the atmosphere, and it's absorbed by these gases and re-radiated back, causing a warming effect for the whole planet. So the short waves pass through, but the gases absorb long wave radiation and re-radiate it back to Earth. You must talk about this short wave and long wave in your answer in the exam if this question comes up, rather than just talking about it absorbing any kind of heat and radiating it. You must be talking about short waves going through, but the gas is absorbing and re-radiating the long wave radiation back. So carbon dioxide then, main driver, all of the burning of fuels and things like that, complete combustion, producing carbon dioxide, a lot of the industry that we're using. Main causes really are industry, so burning fuels, and the increased reliance on fossil fuels. Also deforestation, agriculture, so lots of methane produced by cows contributing, and waste, so decay and the aerobic respiration that's involved in decay, producing carbon dioxide as well. And the consequences of this are quite devastating. They include lots of shifts in weather patterns, so increased or decreased rainfall in areas, increased temperature and changes in temperature patterns. They're causing species of animals to migrate and redistribute in different areas of the planet because they are not adapting well to the changes in the environment. Okay, so try and link the causes to the consequences of the greenhouse effect and overall the effect that we call global warming. In relation to carbon dioxide as well, we can calculate, it's quite difficult, but we can calculate the amount of carbon dioxide and other greenhouse gases released over the full life cycle of a product or event. So you could be talking about the production and manufacture and distribution of a mobile phone. Okay, how much CO2 is that going to produce? You could be talking about a concert. You could be looking at all the people going to the concert, all the transport they're using, all the lighting, all the electricity. How much is that going to cost in terms of CO2? And we calculate that and record it as the carbon footprint. And you can look up major companies and they have calculated their carbon footprint and published it. They may well only publish snippets, okay, it may well be a bit biased, but you can work out how much carbon dioxide they are using. Other changes to the environment then. We've got solid particulates. When we burn things in incomplete combustion, you can get a bit of carbon out, a bit of soot. Okay, carbon or soot going into the atmosphere, and that causes global dimming. In the east, that causes major problems. It blocks the sunlight coming through and causes some serious health effects by breathing in solid particulates. So global dimming is what's caused by that. Carbon monoxide is a big problem. That's created in incomplete combustion when there's not enough oxygen. That is creating the toxic carbon monoxide. So if you breathe that in, that's toxic and that can kill you. These two, sulfur dioxide and nitrogen oxides, can all contribute to acid rain. If you have impurities in your fuel, such as sulfur, if that reacts with oxygen, that's going to make sulfur dioxide. And those, when they go into the atmosphere, can contribute to acid rain. Nitrogen oxides are made in very hot conditions inside cars when you're burning fuel. So these are made in those extreme conditions, but they can also contribute to acid rain. We've made it to the final topic, ladies and gentlemen. Topic 10 for chemistry is all about how we use resources, and that relates to a lot of the stuff that's in topic 9 as well, with what we're doing to the planet. First of all, let's have a look at this definition. Can you think of what the word is that I'm looking for that is described by development that meets the needs of present society without damaging future generations? Well, the development we're talking about is sustainable development. So when we're planning for new products, new buildings, new communities, we now really need to think sustainably, okay? And what we would do is we would perhaps produce something called a life cycle assessment to make us really think about how we're using resources and the impact that they're having on the environment to make them as sustainable as possible. And there's 4 processes in that. There's looking at how we obtain the raw materials. So are we using big machinery, releasing lots of CO2? Do we have to use big lorries to then transport what we've mined, back to a factory or something like that? Does it create a big impact on the environment? Does it make it an eyesore with all the products you've extracted? Are they toxic? Then we look at the manufacturing and packaging. How much CO2, sulfur dioxide are we releasing into the environment when we're packaging? How much electricity are we using? Things like that. Then we look at when we use it. Do we just use it once? Can we recycle it, or is it just a one-time thing that we can use? How long will it last for? Things like that. And then we look at how we dispose of it. Is it going to contribute a lot to landfill and methane being released from the landfill and things like that? Carbon dioxide. How are we disposing it? By lorries? What are we doing? So we look really in depth about a whole life cycle assessment, and you can do this for anything. You could do this for a computer. It's a great computer there, I think. You can do that for a computer. You can do it when you're just processing a book and making a book, and that is where my drawing limitations end. So we'll leave it there. But any project or objects that you're thinking about, you can create a life cycle assessment for. In the exam, this is where they may well ask you that evaluate question. So they might get you to compare 2 different bags, for example. In the spec, they want you to look at paper bags and plastic bags, and they may well give you some information, but also use your own knowledge as well. Evaluate would mean that you would need to put advantages or pros and cons and disadvantages, and you must finish with a justified conclusion. So let's say we're evaluating the use of paper versus plastic bags. You'd think about all the different processes in the life cycle assessment. You'd give advantages of each, disadvantages of each, and then you would finish with a justified conclusion. Now, the mark scheme's not going to say what's right or wrong. So if you come out and said, I think paper bags are best, and someone else said, I think plastic bags are best, that doesn't matter, as long as you justify your conclusion and say why. So, last little bit then for topic 10 is to do with water. So this word, potable water or potable water, however way you'd like to say it, potable or potable water is water that is safe to drink. If you can It doesn't have to be pure, okay? So I'll add here, not necessarily pure. It just needs to have a low number of microbes and salts to be able to be potable and safe to drink. So to make water that is safe to drink, we're not necessarily going to have pure water, but we're going to have some sort of water source. So we could be extracting water that's fallen on the surface or perhaps from the ground. It depends where you have water available in the country that you are living in. We'd first have to filter that water. That's pretty obvious. It's going to have a time through a mesh to filter any of the large pieces, so twigs and plastic bags and whatever else is in that water. And then it's going to go through a finer filter of sand and gravel. And that's great because we now end up with some water that looks okay. It's been filtered. It looks colourless. However, it's probably going to have some nasty microbes in there that could make you feel ill. So the last process is sterilisation to kill microbes. And there's several ways that you can do that. You can use UV radiation, ultraviolet radiation. You can bubble through some gases such as ozone or maybe chlorine. And that will then make it potable and safe to drink. If you did want to make pure water, which you could do, you would use distillation. And we've gone through that in the required practical, where you'd evaporate the water, condense it, and this would actually be pure. But this is expensive because it costs a lot of energy. You're having to heat up the water, whereas this, you're just letting it filter through some mesh and some sand and gravel and then putting some sterile fluids in or sterile gases in. In this case, it's expensive because it takes lots of energy. So we really don't want to do that unless we have to. Some countries might have to. Imagine if you lived in a really dry country where there's not a lot of surface water, not a lot of groundwater. You may have to use distillation or something called reverse osmosis. This is really new technology. Let's look at this picture. We've got water molecules in blue and salt molecules in orange. Normal osmosis would see the water move in this direction, from the dilute to the concentrated, from where there's more water to where there's less water. However, reverse osmosis says what it does on the tin. The osmosis goes in the other direction. So actually, it goes against the concentration gradient and the water molecules move in this direction. To do that, you're going to have to provide a lot of pressure this way, okay, for that reverse osmosis to happen, and it will have to go through a special partially permeable membrane in the middle. Now that's useful for countries where they've got a lot of ocean, they've got a lot of salt water. They don't want to do distillation because it's expensive, but they might be able to do this reverse osmosis instead to get the water from the salt water. Final thing then is for combined scientists, and then I'll go through the higher tier content, is what we do with all the water that we flush down the toilets, that we get rid of from our baths, because that all has to be recycled and used again. First thing it does is really go through another filtering process, whereby we call this screening this time. So in this screening process, you look at the water and you remove any large objects. So it could be for a filter or a little net or a machine going through, removing any large objects that are in there. It's then left in really big tanks called sedimentation tanks. And at this point, this process of sedimentation, all of the solid, heavy parts of the water, so let's say we've put our water in there. It might look okay, but it's going to be full of sludge and waste and horrible stuff. Well, it won't look okay, actually. It will smell and it'll look horrible. But all of the solid stuff goes to the bottom and makes a sludge at the bottom, because that's the heavy sediment that falls. And at the top, you get this kind of more fluffy, light effluent that sits on top, and it gets a bit foamy and a bit smelly and a bit horrible. So the sludge we can put an anaerobic digester. So if you were doing separate science, you would have looked at biogas generators in the separate only content. So with anaerobic digestion, you can then take that sludge and make it into really useful products such as fertilizer and put that onto the soil, or natural gas. So you can make methane from this and use that as a fuel. Effluent then on top, you can do aerobic digestion of this, where you allow natural microorganisms to respire aerobically, and then that can then be released back into the rivers and the water courses that go around. So when we get our dirty water, we take away the large objects through screening, we put it in big tanks, allow the sludge to fall at the bottom. It's called sedimentation. And then either for the sludge, we do anaerobic respiration, and for the effluent, we do aerobic respiration. So if you are doing combined science foundation, that is where we finish with the chemistry revision video. And I do wish you all the best of luck for your exam tomorrow. And thank you very much for watching. If you're doing higher tier, then I will highlight for you the higher tier content that will come up in tomorrow's exam. So nice when you look at a screen and there are only a few things on the screen. So you really need to nail these down if you're doing higher tier only. So you need to calculate the rate of a reaction using the gradient. You need to know about equilibrium and the Chatelier's principle in terms of reversible reactions. And you also need to know about phytomining and bioleaching. So, calculating a gradient from a graph. This question says, what is the rate of reaction at 8 seconds? So, this time we need to use a tangent to calculate the rate of reaction. So, at the point of 8 seconds, what you need to do is draw a line as close to the line as possible. So it's meeting there at 8 seconds at this point here. It's meeting there and it is close to the line as possible. There will be some degree of variation in your answers with this question, and there'll be a certain tolerance that you have to fall in. So when you calculate the gradient, just like you would do in maths, you would find a sensible point where they are kind of crossing the lines, and you would do your change in y, delta y, divided by your change in x. So in this case, we would be looking at the difference between 35 and 20 for our change in y, so 15, divided by the difference between 2 and 12, which is 10, which makes it nice and easy for me. So 15 divided by 10 would give us an answer of 1.5 centimeters cubed per second. So make sure you can do that if you're doing higher tier. The next big section for higher tier is equilibrium and the, oh, I've gone English there, look. It should be Le Chatelier's principle. Okay, so Le Chatelier's principle is simply the idea that when conditions of a reversible reaction change at equilibrium, the system will respond to counteract that change. And to reach equilibrium, we must be talking about a closed system. And in a closed system, no reactants can get in and no products can get out. So when conditions of a reversible reaction change at equilibrium, the system will respond. So these are the three things that we're going to talk about. This is a reversible reaction just here. This is the actual one for the Haber process if you're doing separate science. So we've got 1 mole of nitrogen, 3 moles of hydrogen, and 2 moles of ammonia. With concentration, it's simple. If you increase the concentration of your reactants, then your concentration of your products increases because it's trying to counteract the change, and that means that this will decrease again. So if you increase the concentration of your reactants, the Chatelier's principle says that the concentration of products will also increase, and because this will increase, then the concentration of the reactants will go down, and that's counteracting the change. So if you increase the concentration of the reactants, concentration of the products will go up, that will start breaking down more into that, and then you'll eventually decrease the concentration of reactants, hence counteracting that change. Temperature will depend on whether the reaction is endothermic or exothermic. In this case, it's easy to spot because this is your one molecule. That means that's breaking down into two, and that is an endothermic reaction. So in this direction, it's endothermic, and in the opposite direction, it's exothermic. So temperature favours the endothermic reaction. So because this needs heat to break it down, you need to take in heat to break this molecule down. So if you add more heat, if you increase the temperature, you will favour the endothermic reaction, and therefore this will break down and produce more reactants. So in this case, the example of the above, we say the equilibrium will shift to the left. And at this point, just a reminder, the equilibrium is the point where the rate of reaction is the same on both sides. Not the amount of things, but just the rate at which they're being made on each side. So if we increase the temperature, the equilibrium in this case will shift to the left and we will produce more product. So with pressure, we have 1, 2, 3. So in this case, if we increase the pressure, then we are going to favour the side where there are more molecules. Okay, so if we're increasing the pressure, we're going to favour the left-hand side of this reaction because there are more molecules. So all we need to look at for this one is the numbers that you have here in front of the molecules, and that will help you. So in this case here, we've got this being favoured because of this side we've got 4 molecules or 4 moles compared to 2 moles on this side. So in this case, if you increase the pressure, you will increase the forward direction. So you'll get an equilibrium shift to the right. Okay, and that is what you need to know for the equilibrium and Le Chatelier's principle. So concentration, temperature, pressure, count how many moles there are for pressure, work out which one's exo and which one's endothermic reaction, and then you can work that one out. So the next extra bit is phytomining. So with phytomining, we are using plants, P for phytomining, P for plants, to extract minerals. Now, we want lots of different metals, but unfortunately, good high-grade ores of metals are running out. So resulting in having to use low-grade ores with, for example, not a lot of copper in. If we wanted to extract copper, we could then grow plants on these low-grade ores. These plants would take up the copper compounds, and then they would be stored within the plants. What you then do is harvest the plants and chop them, and then you would burn them. And when you've harvested and burned your plants, you would then be left with ash that contains your copper. At this point, you can't easily extract the copper because it's not magnetic, so you can't use magnet or anything like that. So there's a couple of processes you could use. You could add sulfuric acid, H2SO4, and that would make copper sulfate, CuSO4, and then you could do electrolysis to extract the copper, and that came up in topic 1, that process. You won't need to go in depth for the process, but that's what you might be able to do. Or you can do a displacement reaction with some scrap iron. That's the cheaper one. So if you have your copper sulfate, you can do your iron, add your copper sulfate, and that will make iron sulfate plus copper. And there you have it extracted. So that's phytomining, using plants, burning them, extracting the copper afterwards. So bioleaching, similar process, but using B for bacteria. So this time you've got your bacteria, which you grow on your low-grade ore. So you've got your bacteria. And this time the bacteria break down the copper compounds that are in the ore. They use the energy from that, and then they produce a leachate solution. You don't need to know this in detail, but you need to know that the bacteria break down the copper compounds and produce a solution called leachate. And then exactly the same as you did before with the plants, you would either use electrolysis or you would use displacement with scrap iron to extract the copper from that. So that is it for combined science. That's the higher only content for combined science that you need to know. The next bit that I'm going to do is for separate scientists. So if you're doing higher combined, all the best for tomorrow. Really hope the exam goes well, and I hope that's helped you a little bit. If you're doing separate science, I'll just have a look at the wall and see if there's any questions, and then I'll go through a couple of the separate bits. Okay, so one question for the separate science as we go on is, do we have to memorize the displayed formula for glycine when talking about amino acids? With glycine, it'd be very harsh if they asked you to draw hard glycine. I don't think they will do that, but you will need to know the two groups to go with glycine. So you will need to know the carboxyl group and the amino group, and the fact that when they join together to make a polypeptide, that the carboxyl group of one amino acid joins with the amino group of the other one, and so on, to make a long chain polypeptide, which is folded into a protein. So it'd be very harsh if they asked you to revise the displayed, to write the displayed formula. So my advice would be that that wouldn't be where your revision would need to be concentrated for that one. More the fact that you need to know that they've got two different groups for the condensation polymerization. So any more questions you got put on the wall? I'm not going to go through all of the detail for separate science because I have created a video earlier on today, which I've uploaded. So if you study separate science for the hour and 45-minute exams, then please watch that video, or if you want to watch that video, you can do. Some people watch it in faster speed, so I think there's an option to do that. So if you want to go through it a bit quicker, you can do that, but it's approximately an hour long, and it goes through all the separate science content. It's important to know what this is, because when it comes to your exam, you've got an extra 30 minutes worth of questions, so they will ask you separate only content to make you different from the combined scientists. So these are the contents that you need to know. You need to know alkenes, those hydrocarbons with a double bond, more organic chemistry, alcohols, carboxylic acids and esters. You need to be able to draw them. Polymers, so addition polymerization and condensation polymerization, and like the question I was asking about amino acids making polypeptides. Materials and their properties, so things like ceramics, glass, metals, alloys. Corrosion and the conditions needed for rusting. Haber process, now that links into Le Chatelier's principle and changing conditions. NPK fertilizers, which is quite involved, where you get the nitrogen, phosphorus and the potassium from. Flame emission spectroscopy, is an instrumental method, a machine method for testing for ions. And the bit that I'm going to go through now is the required practical on testing for ions, because it's quite likely that they will ask you questions on that in the exam. In the separate science only video that you can watch elsewhere, I have told you which bits are higher tier only as well. There's not many bits. I'll just go through that now, actually, before I go through the other bit. These are the bits that are higher tier only. So really have a look at this slide. If you're doing higher tier, expect these things to come up. So condensation polymerization, condensation polymerization, explaining why carboxylic acids are weak. So talking about the fact that they only partially ionize in water. Polypeptides, again, condensation polymerization, but amino acids making polypeptides, and interpreting graphs of different conditions and rate of reaction. So you're going to have a graph with multiple rates of reaction on, and you need to be thinking about what conditions are causing these. They'll put some data involved, link it with Le Chatelier's principle and pressure and temperature and things like that, and you need to be able to interpret those. So that's for higher tier. For now, what we're going to go through is just the identifying ions required practical, because it's quite involved. It links in with the water stuff and distillation that we talked about earlier. So last bit then, identifying ions. So we need to know the flame test. To do a flame test, you will get a metal loop and you will dip it in acid and then put it in a flame just to make sure it's completely clean and there's no other compounds on there. The whole reason you want to identify ions, let's say you had a random powder and you wanted to know what it was. Well, it's probably going to be some ionic substance because we're measuring ions. So it could be sodium chloride. It could be potassium sulfate. It could be absolutely anything, and you need to work out what it is by doing these tests. Now, one of the tests that we're looking for is the cation, which is the metal, so sodium or potassium, and the other test we're looking at is the anion, which is the negative bit, the chloride or the sulfate or whatever it is we're looking at. So that's just to put it in context. When we're doing these tests, this is why we are doing them. So the lithium produces a crimson flame. So you've dipped it in your acid, you dipped it in the flame, then you put it in your sample, and then you put it into the flame. And if it goes crimson, that's lithium. If it goes yellow, that's sodium. Potassium is a lilac colour. Calcium is an orangey red colour, mainly red really, and copper is green. That's great, but there's a big problem that I expect them to ask you about, because they often do, and that's about masking. If you try and put a substance into a flame, but there's two things in it, let's say there's calcium and copper, well, you might not be able to see the copper because the green flame may be very light and it may be masked by the dominant red flame in there. So flame tests aren't 100% perfect because of that reason and because of masking. What you could do just to make sure, or as an alternative test, is to add sodium hydroxide to your compound, and that will produce a precipitate. If you produce a blue precipitate, that is copper, iron 2, which is Fe2+, as opposed to iron 3, which is Fe3+, would produce a green precipitate, iron 3, a brown precipitate, and these three down here, calcium, aluminium, and magnesium, will all produce a white precipitate. Now, the aluminium will disappear if you add excess sodium hydroxide. This will disappear, and that's how you know that one will be aluminium, and the rest of the two will stay. And you might have to do a flame test or another test to work out that that is calcium. If you do a flame test, you can work out that if that goes orange red, you've got calcium. If not, you've got magnesium. But aluminium will disappear. One way to remember that is if you remember, like I do, that the American version of aluminium is aluminum. And for me, that sounds like a little Harry Potter spell, where when you say aluminum, something is going to disappear. So if you have a crazy brain like me, you might need to remember that aluminum is the one that disappears if you add excess sodium hydroxide. So aluminum to the text. And here we go. Last little bit then. The anions, the carbonates, the halides, and the sulfates. To work out whether you've got a carbonate, you would add dilute acid and bubble the gas through lime water. And you've guessed it, if the lime water goes cloudy, you have a carbonate. So it's a positive test for a carbonate if your lime water goes cloudy. You might be looking to see whether you've got a halide. This is an ion from group 7 from the halogen. So these are the three that you need to know: chlorine, bromine, and iodine. So to test for a halide, you would add a little bit of dilute nitric acid and silver nitrate. And when you do that, you get a precipitate. So you would get silver chloride, silver bromide, or silver iodide. And this is white. As you go down group 7, it gets darker. So bromine is cream. That might help you remember it. And iodine is yellow. So as you go down the periodic table, these precipitates get darker. So this would be silver chloride, silver bromide, and silver iodide. Final one then, sulfates. You would add dilute hydrochloric acid and barium chloride. Adding this acid really just helps to clean the sample to make sure that there's nothing else in there. And then we can add our barium chloride. And it's the barium that's important. The barium ions from the barium chloride, if sulfate's present, well, they react with them. And this makes a sulfate, a barium sulfate, which is a white precipitate. So you will know whether you have a something sulfate if when you add this, you end up with a white precipitate, which is barium sulfate. So that's the extra required practical that I expect to be coming up at some point within some questions within the exam, because it's quite a lot of content for that one. If you do want some more information on the separate science only stuff, then please check out the other video. I really do hope that this has been useful for you. And I will check the wall a few times to see if there are any further questions to go through. So I'll hang on for a couple of minutes. But if not, all the best for tomorrow. And I really hope the exam goes well for you.